Right now, 15 billion miles from Earth, a machine the size of a car is screaming into the void. Its signal is weaker than a refrigerator light bulb. It takes 22 hours to reach us. And somehow, we can still hear it. This is how we talk to something that left the solar system. September 5th, 1977, Cape Canaveral, Florida. A Titan Centaur rocket launches Voyager 1 into space. The mission plan? Explore Jupiter and Saturn. Then, shut down. Expected lifespan? 5 years. That was 47 years ago. Voyager 1 is still transmitting. Let's put its distance into perspective. The Moon is 240,000 miles from Earth. Light reaches it in 1.3 seconds. Mars? 140 million miles away. Light takes 20 minutes. Voyager 1? 15 billion miles. A signal takes 22.5 hours, one way. If you sent hello to Voyager right now, you'd get a response in 45 hours, almost 2 full days for a round-trip conversation. But here's the really insane part. Voyager isn't standing still. It's moving at 38,000 miles per hour. That's 10.5 miles every single second. While you read this sentence, it traveled 100 miles farther from Earth. Every day, it gets 900,000 miles more distant. Every year, another 330 million miles. And we can still hear it. How? Voyager 1 has a 12-foot dish antenna. That's it. Smaller than a satellite TV dish. It transmits with 22 watts of power. A refrigerator light bulb uses 15 watts. Your phone charger? 20 watts. Voyager is sending signals across 15 billion miles with less power than it takes to charge your iPhone. Now here's where physics becomes cruel. Radio signals follow the inverse square law. Double the distance, the signal becomes 4 times weaker. Triple the distance, 9 times weaker. By the time Voyager's 22-watt signal crosses 15 billion miles of empty space, it arrives at Earth with a strength of 0.00000000000000001 watt. That's a billionth of a trillionth of a watt. To put that in perspective, if you collected all the energy from Voyager signals that have ever reached Earth, it wouldn't be enough to melt a single snowflake. So, how do we detect it? NASA built the Deep Space Network, 3 locations around the world: California, Spain, Australia. Each has massive radio dishes, 230 feet across. That's a 20-story building lying on its side. These dishes are so sensitive, they could detect a cell phone signal from Jupiter. When Voyager transmits, the Deep Space Network locks onto it, filters out cosmic noise, amplifies the signal, decodes it, and somehow, impossibly, we hear what Voyager has to say. But even with these monster antennas, there's a problem. Voyager's signal is getting weaker. Every year, it fades a little more. Not because the distance increases, though that doesn't help, but because Voyager is dying. Voyager doesn't have solar panels. At its distance, the sun looks like just another star. Solar power is useless. Instead, Voyager uses 3 nuclear batteries, radioisotope thermoelectric generators, RTGs. They convert heat from decaying plutonium-238 into electricity. At launch in 1977, Voyager 1 produced 470 watts of power, enough to run a desktop computer. Today, 249 watts, and dropping by 4 watts every year. NASA has been playing a brutal game of triage. What do we shut down? What do we keep? In 1990, they shut down Voyager's cameras. The last photo it ever took? The pale blue dot. Earth seen from 4 billion miles away. A single pixel of light in an ocean of darkness. After that, the cameras were permanently turned off to save power. Over the years, more systems died. The ultraviolet spectrometer, the infrared interferometer, the photopolarimeter. Today, only 4 of Voyager's 10 scientific instruments still work: magnetometer, plasma science experiment, low-energy charged particle detector, cosmic ray detector. That's it, 4 instruments, clinging to existence on 249 watts of decaying power. But here's the terrifying math. At 4 watts per year, Voyager will drop below 200 watts by 2030. NASA estimates that's the minimum needed to keep transmitting. After that, they'll have to start shutting down instruments, one by one. The magnetometer might go first, then the plasma detector, then the particle sensors. By 2036, all instruments will be off. Voyager will have just enough power to transmit its position and basic telemetry. And by 2040, silence. No more data, no more signals. Just a cold, dead machine hurtling through interstellar space forever. Voyager has almost died multiple times. 2023, the antenna drift. Voyager 2, the twin spacecraft, suddenly went silent. NASA checked everything. The Deep Space Network was working, the spacecraft was still there. Then they realized Voyager's antenna had drifted 2 degrees off target. 2 degrees. That's less than the width of your finger held at arm's length. But at 12 billion miles away, 2 degrees means the signal misses Earth entirely, like aiming a laser pointer at a penny from 10 miles away. Communication was lost, completely. NASA had one hope. Voyager was programmed to auto-correct its orientation 4 times per year. They waited. Weeks passed, nothing. Then, on schedule, Voyager rotated itself back. The signal returned. Crisis averted. Barely. Voyager 1 started sending gibberish. Not data, just random ones and zeros. For 5 months, NASA had no idea what Voyager was trying to say. Engineers traced the problem. One of Voyager's 3 onboard computers had corrupted memory. A single chip, 47 years old, finally failed. The spacecraft was trying to route data through that dead computer. NASA sent a command, switched to backup computer. 22 hours later, the command arrived. Voyager processed it, switched computers. 22 hours after that, Earth received confirmation. Total time to fix, 45 hours. Across 15 billion miles, using 1977 technology. It worked. The thruster problem. Voyager uses tiny thrusters to keep its antenna pointed at Earth. They fire in short bursts, just milliseconds, to adjust orientation. These thrusters have fired billions of times since 1977, and now they're clogging. Fuel residue builds up inside the lines, like plaque in arteries. Eventually, they'll fail. NASA's solution? Update the software to make each thruster burst last longer. Fewer firings, less wear. They uploaded the patch from Earth to a spacecraft 15 billion miles away, running on a computer with 69 kilobytes of memory, less than a single tweet. It worked. Engineers estimate it bought Voyager another 5 years. NASA estimates that's when Voyager 1 will send its last coherent message. What will it say? Probably nothing poetic, just telemetry, numbers, its position, battery voltage, temperature readings. Then one day, the signal will stop. Not because Voyager crashes, not because it breaks apart, but because it runs out of power. The plutonium core will decay to the point where it can no longer generate electricity. The computers will shut down. The transmitter will go dark. And Voyager will continue, silent, forever. It'll drift through the Oort cloud for the next 30,000 years, then exit into true interstellar space. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. It won't stop, it'll just drift by. A dead relic from a species that once looked up at the stars and wondered what's out there. By then, humanity might be extinct, or we might have spread across the galaxy. Either way, Voyager will still be out there, carrying the golden record, a time capsule of human civilization. Music, greetings, images of Earth. A message to anyone who might find it. We were here. We existed. We reached for the stars. Voyager 1 has sent back data for 47 years. Here's what it found. Jupiter has faint rings. We didn't know. Io has active volcanoes, the first ever found beyond Earth. Titan has a thick atmosphere, potentially habitable. The heliosphere has a boundary. We crossed it in 2012. Interstellar space has magnetic fields, which we're measuring right now. All from a machine built in the 1970s, with 69 kilobytes of memory, less than a single tweet. And we're still talking to it. In 12 years, we'll lose contact with Voyager 1. Forever. But for now, 15 billion miles away, a tiny machine is screaming into the darkness, and we're listening.